Let C be the unit circle, center 0, radius 1, traversed counterclockwise. There's our orientation arrows. Compute the contour integral around the unit circle of e to the z over z to the fourth dz. And for this, we will use Cauchy's integral formula, which is this formula here, which has an integral in it that is very similar looking to our integral. We have some function divided by z minus z0 to a power. So the first thing we might notice is that our z0 here appears to be 0 because we have z to the fourth as opposed to z minus something to the fourth. So the something that's being subtracted appears to be 0. And then that power, n plus 1, is 4, so n is 3. And then the function f of z is the e to the z in the numerator here. So this formula is telling us that the value of a function at a point is equal to this coefficient times this integral, and we're assuming that the function is analytic along and inside a positively oriented simple closed contour that contains the point z0 inside. So in our case, we have a positively oriented, because it's counterclockwise is positive orientation, the unit circle, so it's a simple closed contour. And the unit circle contains the point 0 as its center point, so in its interior. And this represents the nth derivative at z0. So the nth derivative of the function evaluated at z0 is equal to this coefficient n factorial over 2 pi I times this integral. So this is Cauchy's integral formula. It's a little bit of a complicated formula, but it's pretty easy to use once we identify all of the parts here. So we've identified z0 as 0, because this is the same as z minus 0 to the fourth, of course. And the power is n plus 1, so n plus 1 is 4, which made n 3. And then f of z is e to the z. And e to the z is an entire function, so it is going to be analytic along and inside any contour. So we don't have any issues with the hypotheses of the formula, so we can go ahead and use it. So solving for the integral, I'm not going to write the whole thing here, is equal to 2 pi I divided by n factorial times the nth derivative at the center. So our integral is equal to 2 pi I divided by 3 factorial times the third derivative of our function evaluated at 0. But if f of z is e to the z, then f prime of z is also e to the z, and all of the derivatives are e to the z, so the third derivative in particular is still e to the z. So the answer is 2 pi I over 3 factorial times e to the 0. We have to plug in the number z0, which is 0 in this case. And e to the 0 is 1. So simplifying, this is 2 pi I over 6, or pi I over 3. The value of the integral is pi I over 3, thanks to Cauchy's integral formula.